So normally I do electric fields in one day, but I'm doing it over 2 days because I think it's so important. We just said that there was two ways to define the electric field. The first way is if you knew the charge that was creating it. And we compared this to gravity, Andrew, if you knew the planet. You could calculate electric field with kq over r squared. The second way, Zay, was if you didn't know the planet that was causing it, but you could detect it by putting a charge inside the electric field somewhere. It was the force divided by the charge at that location told you the electric field. And this gave us our units for electric field, newtons per coulomb. The only area that this started to get different from gravity was gravity, everything falls down, but with electricity, things can fall up because like charges can repel. So we said we need to define the direction. We said the direction is which way would a positive test charge want to go if it could? Or the shorter version was from positive to negative. We said we represent electric fields with lines. Arrows tell you the direction of the field. And we left off right here. You ready? I like example 6. Example 6 I guarantee is going to be on your test. I'm going to give you more than one charge, probably two. And I'm going to say, find the net electric field at a location somewhere between them. So, to determine the electric field of two charges, the principle of superposition, that's a fancy phrase, it says, look, you find the vector sum of the field of the individual charges. In other words, if I want to find the net electric field right there, don't write this part down. Temporarily, I'm going to ignore that. Don't scribble that charge out. I'm going to call this, oh heck, charge 1. I'm going to call this charge 2. And what I'm going to do, Brianna, is I'm going to find the electric field from charge 1, magnitude and direction. I'm going to find the electric field from charge 2, magnitude and direction. And then I'll add them vectorially. It won't have to be tip to tail because they're not at angles. I'll just say if they're in the same direction, add them. If they're in opposite directions, bigger minus smaller, and the bigger is the direction. Okay. Which equation am I going to use for electric field? Well, the electric field right there is being caused by charge 1. This is your planet. I'm going to use kq1 over r1 squared. What was k, Zay? Yeah, that's one of the easier constants to remember. 9 times 10 to the 9th. Q1 is 1 microcoulomb. That's 1 times 10 to the negative 6. Almost ready to go, Em? Okay. House clean later. You'll have time later. Divided by, what's R1? Oh, that's convenient. 1 squared. How big is the electric field at this location that charge 1 is creating? Call me silly. Aren't you going to get 9,000? Because isn't it 9 times 1 divided by 1? And then it's 10 to the 9th times 10 to negative 6. And you can just add the exponents. And actually, it's my 1 times table and a 9 there. Double check me, but I'm pretty sure it is 9,000. Yes? Units? Units? Newtons for every coulomb, per coulomb. Direction. So again, ignore this charge. If you were a tiny positive charge right there, how tiny? So tiny that you don't have your own electric field, because that would change the question. Based on this guy, which way would you want to move if you could? Left, right, up, or down? What is this charge right here, positive or negative? And we're putting an imaginary positive charge right there. That's how we defined it. So which way would we want to move? What does that mean, Brett? Okay. The electric field on the second charge is going to be kq2 over r2 squared. Have I mentioned I like this question, like this question, like this question? Okay. I'd like to find the net electric field there. That's going to be 9 times 10 to the 9th Also 1 times 10 to the negative 6 divided by, oh, I got to be careful. I was almost going to write down 4 squared, but it's not. This whole distance is 4. This distance is 1. What's that distance there? It's going to be 3 squared. And once again, I'm going to argue, Brett, that I don't really need a calculator, because isn't this going to be 9 divided by 9? Yes? And you're just going to have a 10 to the 9th times a 10 to the negative 6. I think the answer here is 1,000 newtons per coulomb. Direction. Right here, based on this charge, which way would a tiny positive charge right there want to move if it could? Left, right, up, or down? Brianna. So, the net electric field, or the total electric field, well, what do you think 9,000 right plus 1,000 left is going to add up to? Think about it. We've done vector math. Connor. 8,000 newtons per coulomb right. What if they were both to the right? It would be 10,000 to the right. Okay, do you see what I mean by add them vectorially? And remember, electric field is a vector, which means I'm going to want the direction every time too. Okay. Example 7 says, draw approximately the resultant electric field at the indicated field points. Both charges are positive 1 microcoulomb, like example 6. Okay. These ones are going to be tougher and yuckier. Let's do the ones that are in a nice straight line first. In fact, I think right here, I would have charge 1 pushing to the right, charge 2 with an electric field to the left. Are both these charges the same? Are both these distances the same? Then Jacob, what can you tell me about the electric fields? They are the same magnitude but opposite direction. You know what my net electric field is right there? Nothing. Is that okay, Mitch? And what about right here? Well, this, because I'm closer, would give me a strong electric field that way. This would give me an electric field to the left, but it wouldn't be as strong because I'm further away. I have strong to the right plus weak to the left. If I add those together, which direction is left over? Smaller to the right. And I think we could make the same argument over here. We would say, hey, look, this guy has a strong electric field left. This guy has a weak electric field to the right. Strong left plus weak right. I think your net electric field would be pointing that way. Is that okay, Emily? Let's do this one, because I think this is easier than this yucky one. Here, pretend this charge is no longer there. Which way would a positive test charge want to move if it could because of that guy? What direction is the electric field? Zay, you're right. Yeah, I think this way. And what direction is the electric field because of this guy? That way. Okay, how would I add those two together? Yeah, I think tip to tail. I think what you would have is, and I should have been consistent in my colors, I'll go with red. That way and that way. If I add this plus that, you know what? I think you end up with an electric field and a net force straight up, because the electric field tells you the direction of the net force. Whatever direction the electric field is, that direction, Emily, is your force. This charge here would get pushed straight up. I don't know how big, but that's my net electric field. So let's see if we can puzzle this one out then. Which direction is the electric field because of this charge, the left-hand charge? What direction is the electric field right there? Jacob? Straight up. What about because of this guy? this way. You know what? I'll even add them vectorially right away. Yeah, you know, I think the resultant would be kind of like that. Almost straight up, but a little bit to the left. And that means if I put a proton right there, it would start to move in that direction. Okay. This brings us to our bonus video game. Unfortunately, I don't know if I'll put it on the website. I'm going to tell it to you right now. And the instructions on how to get there will appear later on in the handout, so don't freak out. There's a website called PHET, P-H-E-T. It stands for Physics I can't remember what it stands out for. Yeah, Good Physics Sims. So if you go to the PHET website and you click on Play with Sims, like I just did, click on Physics, Electricity, Magnets, and Circuits, and in keeping with the NHL trade deadline, of course, it's going to be electric field hockey. Surprisingly addictive. Let's put this into my Physics 12 folder. I think I have it there already, but we'll see if they've updated it. What does electric field hockey look like? Yes, this is also for some of my hockey players. Okay. What you need to do is you need to send this positive charge into the goal. Now this is level 0. The easiest way to send this positive charge into the goal would either be to put a positive right there so that it gets repelled. Okay. Or I could put a negative charge right here so it gets attracted. Oh, wait a minute. Once it goes past, the electric field's in the opposite direction, isn't it? Okay. Maybe I'll put a negative right there. Oh, I should put it right there. Okay, that's level 0. Level 1, you have to bank it around the wall. So I might start by putting a positive right there. And then maybe I'll put another positive right there, so I'm hoping it'll kind of get deflected. Oh, let's put a negative right behind the goal to attract it into the net, maybe. Ah! A little too much deflection. Let's put it maybe there. And you'll notice just that small change gave me a completely different result. Okay. Put a positive right there. Now, you might think that that'll deflect it. The problem is, not only will it deflect it right here, it's already deflecting it right there. It's going to change how it behaves on this first path, too. It's much more complicated than you realize. Hey, I got level 1. Clear. Reset. Level 2, you get nothing for level 2. If you can get level 3, and here is the condition, you can't bank it off the screen and then back around. That's very easy to do. I've done that. But if you complete level 3 by managing to get the charge to snake its way all the way through here, and you can either take a video or a screenshot, a video is very impressive, then you will get 2 bonus marks on the test. I gotta warn you though, this is a little bit addictive. Really, Mr. Dueck? Yeah. Show you some previous solutions, and I'm not worried about you copying these. Here was one of the first kids to get it. Okay? And I don't know if you can see how many tries it took him. It's surprisingly addictive. I've had kids hand me stuff in with 300 trials before. I just warn you. Because once you get close, it's surprisingly addictive. Are you going to try and take a picture of that or something like that there, Mitch? Ain't going to help you, mister. Okay? Now, the brute force way is to line and build a tunnel almost with charges. And if you do that, that's fine. What I'm also curious to see is who can do it with the fewest number of charges. I think right now the person who's done it with the fewest did it with 12 charges. Okay? Electric field hockey. Back to the notes. We said that we can represent electric fields with lines. So this says draw the electric field pattern for equal like charges. I'd like you to underline the word equal for me. What that means is they'll both have the same number of lines coming from them. So Brianna, if your sketch has 6 lines coming from here, but I have 6 lines coming from here, I usually go 4 or 8 because it gives me nice, easy round numbers, all right? And I think it's going to look like this. This would send an electric field, but it would get repelled. This would send an electric field, but it would get repelled. This would send an electric field that would get repelled like this, like that. This would send an electric field getting repelled, getting repelled. In the middle here, you might have one going like that, going like that. And what we're really saying is, if you put, for example, a positive charge right there, it would get pushed left, but it would also get pushed to the right and up by this guy, which is why eventually it would get deflected this way. Or if I go back to my electric field hockey simulation and go back to practice, here's a positive, and here's a positive. Let's see if I can put them same distance apart. Watch how this behaves. Okay? Now, this is much more complicated because as soon as it moves, the field changes again, and as soon as it moves, the field changes again, and it's a positive charge giving out its own electric field. Hey, let's turn on the field. There is a good example of what the electric field would look like between two like, identical, positive, or same charges. What if they were both negative charges? It would be the same, except instead of the arrows moving away from, you know what the arrows would point? Towards. What about equal and opposite charges? See it? I'll go red because I have to overlap. Certainly, I'd have one line going straight across because the positive would want to move away from this positive and towards that negative. Straight line. If I started in this direction, I would end up bending towards. If I started in this direction, I'd get pulled towards the negative. If I started here, I'd get pulled towards the negative, and I'd get pulled towards the negative. In fact, you could even make an argument, Andrew, that if I went this way, I'd vanish off the page, but I'd end up coming back on the page over here. Don't believe me? See it? See it? Okay. Move it to the center a bit more. Electric field lines. They're great representations of what the electric field looks like. Oh, by the way, Kara, it would also be like this. And like I'll do that so it's kind of symmetrical. Except this is all garbage because, first of all, Mitchell, it's also rating in 3 dimensions. It should be coming out of the page towards us, and now my brain has a tougher time keeping track of all that. It should be going into the paper away from us, right? Because it should be going on in 3 dimensions. And they're not lines. There's an infinite number of lines. But what we did say is the lines are a representation. The closer they are, the stronger the field at that location. Stronger field right there than right here. Now what this does is instead of having the lines be closer, it has them darker. Stronger field, weaker field. Yeah, nice representation. So, the idea of the electric field, turn the page, originated with Michael Faraday, one of my all-time favorite scientists, and I told you I'll go on a long soliloquy about him one day. Among many, 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 many other things, hey, he invented the electric motor and the generator, which basically powers all of our civilization. He was a bookbinder who got hired to be a lab assistant by Sir Humphrey Davies, and Humphrey Davies very quickly figured out, this guy's brilliant. We still consider him maybe the greatest experimentalist of all time. If you needed to design an experiment that would eliminate every other variable and just get the one variable you were looking at, he was brilliant at coming up with great experiments that did that. Brilliant. Very, very poor educational background. In fact, he almost always gave his physics discoveries in English, not in math, because he wasn't comfortable with math. And he also believed if he couldn't say it in a sentence, it wasn't worth, that he hadn't learned it well enough. I told you this a little bit of this already or not? Okay. I also like him because when he died in 1867, he was famous enough that the Queen offered him burial in Westminster Abbey near Isaac Newton, and he turned it down. Very humble. Not that special. I want to be buried in a regular cemetery. I like him. So here's what he said. He represented the field using lines of force which showed the direction in which a tiny positive test charge, how tiny, Brianna? So tiny it doesn't have its own electric field, because otherwise these lines would all change, would want to move if placed anywhere in the field. So figure 11, this shows you the electric field around a positive, the electric field around an electron, the electric field done with computer graphics better than our sketch around one positive and one negative. What if I hadn't told you which one was positive and what if I'd given you this? Hint, hint, I like this question. How could you tell that the left-hand charge is positive and the right-hand charge is negative? Direction of the arrows. That would be a good multiple choice question, I think. Okay. And here are two positive charges. So, in summary, we can find the electric field using the definition if we're told the force on a test. What's the definition? What are the units for electric field? Newtons per coulomb. Force, newtons, per charge, coulomb. If you know that the electrical force that a charge is experiencing at that location, that's one way to calculate electric field. If you don't know how big the charge is right there, but you know how big the planet is, the large charge that's causing the electric field, kq over r squared. Electric field is found by considering a positive test charge away from positive towards negative. Now here's what else this means. We now have two ways to find force. We can find the force by using Coulomb's law. That was lesson 1. Right, Nicole? Or, Nicole, I could also get the F by itself here. And this equation is not on your formula sheet. This one is, but the one I'm about to write is not. It's implied. Get the F by itself. What would I do with that Q? Turns out electric force is whatever charge that's sitting in the electric field times how big the electric field is. And this one drives me crazy because kids forget it, and I'm going to throw this at you on the test. There's going to be a situation somewhere where I say to you, and Mitchell, you look at, this is not on there, is it? Okay. This is, by the way, this used to not be on there. They used to say, oh, for Pete's sakes, it's newtons per coulomb. That's the equation. They have since, only about 5 years ago, added this equation to the formula sheet. It is on, that is on there, yes? Right? This is implied then. Also recall that the direction of electric force is found by asking attract or repel. So we have two ways to find direction. For force, it's like charges attract, like charges repel, unlike charges attract. For electric field, it's which way would a little tiny positive charge want to move that could? Or the short version Emily was from positive to negative. Since force and field are vectors, if we have several charges, then we need to add vectors to find the resultant. What's your homework? Number 1. Number 2. Number 3. Number 6. Number 8. Number 8, I would consider an A or A plus level question. I haven't talked about it. It's saying, where is the electric field 0? What you really want to do is say, when does the first electric field equal the second electric field? And that's your equation. Write an equation for the first electric field. It's going to have an x in it. Write an equation for the second electric field. It's also going to have an x in it. And then solve for x by letting them equal each other. If not, I'll talk about it next class. Number 10. So in number 10, we have a charge that's placed in an electric field. I told you the mass. Find the net force. I think gravity down, electric force up. Winner minus loser. And then once you find the net force, you should be able to also then find the acceleration and find the final. Nice combination of stuff we've done in the past. $11. 13. 15. Now here we're going to find two electric fields, and the net electric field, because they're not in a nice straight line, means we're going to have to add them tip to tail and do some trig. 17. You're giving us a lot. This is crucial. I'm giving you lots of time to work on it too. 18 is nerdily cool. Then, on the very, very final page, here's how you can find your way to the bonus video game. Google PHET, and that should click on the first link. Click on Play with Sims, choose Electricity, Magnets, and Circuits from the left-hand column. Then click on Electric Field Hockey. If anyone can win level 3, Mr. Dueck will give them eternal glory. I'm going to go right-click,